So the next up here is Professor Catherine Heymans from the University of Edinburgh, who's going to give the 2017 George Darwin lecture.
Thank you. Okay, so today we are going to talk about observing the dark side of the universe, which makes me an observational cosmologist. Now, if you got a bunch of cosmologists in a room together, you could broadly split them up into two camps. Now, we'll call the first camp of cosmologists, we'll call them the smug cosmologists, and they are very rightly smug. And that's because this group has brought about a major advance in our understanding of the universe through observations of the cosmic microwave background. Now, I'm sure a lot of you are very familiar with this absolutely iconic image that comes from the Planck satellite. What this blobby map shows you is very small changes in the temperature of the microwave radiation. And this is a relic that's emitted right after the Big Bang that we see as the cosmic microwave background today. And what you're seeing in this image here represents huge step forwards in technology, in instrumentation, in data analysis, theoretical analysis. This is a huge advance. Now, I think a lot of you will have seen this map before, but what a lot of you might not realise is just quite how epic this image is. Because what it shows you is essentially a map of a civil war that was going on right after the Big Bang between two camps, light and matter. Okay, so in the very early universe, you've got the gravity of matter trying to pull clumps of matter together. But in the very hot early universe, the photons, the light, are kind of tied up with the matter, and they kind of resist that squeeze. So where you see hot spots in this map, the red spots, that's where the gravity, the matter's kind of winning and pulling everything together, and that heats up the photons. And then at some point, they're going to be able to resist that squeeze and push those clumps apart again, and that's where you see cold spots. And this sort of civil war, as I like to think of it, is happening all across the universe, everywhere that you look. And what you can do is you can take a theoretical model of exactly how much light there is in the universe, how much matter there is in the universe, the type of matter that there is, and you can do a theoretical analysis to predict exactly how many hot spots you should see and how many cold spots you should see, where different parts, where light or where matter is winning the battle. And that's what you can see in this, there we go, in this image, which I'm sure is something also that you're familiar with because it's the wonderful result from the Planck satellite. Now, what this graph is showing you is just how many hot spots there are and how many cold spots there are and the size of those hot and cold spots. So the first thing that your eye can see on these maps is these sort of little spots, and most of them are small spots. But if you kind of smudge your eyes a little bit and kind of gloss over, you'll see that there are also bigger features as well. And so these different scales are just telling you about how long these battles have been going on in the early universe. Now, this happens in the very early universe, but eventually the universe expands and cools. The light is no longer coupled to the matter, and that's when this radiation is released. It travels all the way through the universe for 13.8 billion years to be caught by the Planck satellite and analysed. Now, the blue spots that you can see here is just the analysis of that data, how many hot and cold spots there are of different sizes. And the red line that you can see here is quite a complicated function, but it has a very few numbers in it. And all we need to know to put into this theoretical curve is exactly how much matter there is and the type of matter, and then there's something else in there. And this is where we come to the smug cosmologist, because they have been able to tell us in an analysis of this data that 4.9% of our universe is made up of ordinary matter. We call it baryonic matter, the stuff that you and I and the Earth and the Moon and the Sun's made up of, the stuff a particle physicist can explain. 4.9% of the universe. Now, then we've got something called dark matter, 26.8% of the universe, dark matter. Now, this is subtly different from the baryonic matter in that it doesn't interact through the electromagnetic force. And so in that early civil war, it wasn't really playing a part. It was just kind of, there, but not really playing a big part. And then what's left, this big part of the pie chart, 68.3% of something that's called dark energy. And we'll come on to later to why it's actually called dark energy, but it's just kind of this extra stuff that is needed. Major advances that we know these numbers now to 1%, to 1 decimal place. That's why this smug cosmology group are feeling smug. This is huge. Now we come on to the other camp of cosmologists who have to explain this result to their mothers and their neighbours. Because this is great, 4.9% of the universe is made up of the stuff we can explain, and the rest? So we'll call the other camp the embarrassed group of cosmologists, because it is quite embarrassing to admit that we do not understand 95% of our universe. And that is the subject of our talk today, is what can we do to understand this 95% of the universe. And the reason why it's interesting, the reason why you should care, is that if you only understand 5% of the universe, it means that you are missing a huge, huge piece of the puzzle. It means that our understanding of fundamental physics at the moment is lacking if we can't explain the majority of our universe. And that's why this is an exciting field to work in. Okay, so I'm going to start off by just getting a sense of the feeling in the room. I've said that we can explain 4.9% of the universe, and then we've got these two other components, something we call dark matter and something we call dark energy. Now, dark matter is the strong gravitational force in our universe. We think it's there from looking at, the first piece of evidence is just looking at galaxies. The stars and galaxies are simply spinning around too fast to hold those galaxies together. If there wasn't dark matter there, the stars in our own Milky Way galaxy would simply fly apart. So I'm going to take a poll with you this evening to see what you think this mysterious dark matter is. So option A, dead or weakling stars that we can't see. Option B, a new type of particle that hardly interacts with the stuff that we're made of, and that's why we can't see it. Option C, a tooth fairy that astronomers have made up because they've got their sums wrong. And I can see, were you raising your hand, sir, for a fourth option? Yes, you would like a fourth option?
Yes, scalar field, free scalar field.
Right. We have an other option. Should we call that another scalar field? Listen, you can only vote for one, and I can see you all. Okay? Who would like to vote for option A, dead or weakling stars that we can't see? Excellent. Thank you, sir. Thank you, sir. B, a new type of particle that hardly interacts with the stuff that we're made up, and that's why we haven't seen it yet. Yes. Okay. Excellent. A tooth fairy that astronomers have made up because we got our sum wrong. Excellent. That's excellent. I'd just like to note that the eminent Professor Richard Ellis voted for that option after spending the majority of his career working on dark matter. Thank you, Richard. And finally, D, other. Excellent. Excellent. For the first option, dead or weakling stars, this was actually the first project my first ever research project was to go out and try and find loads of brown dwarfs to make up the dark matter problem. But now we have such good multi-wavelength data, and also looking at something called micro-lensing, which allows you to really see if there's this stuff there. It really can't be these dead or weakling stars. So that leaves us with B and C. And other, of course. For the purposes of this talk, we're going to go with option B, which is the standard consensus in the community that there is a new type of particle that hardly interacts with the stuff that we are made up of. And if we take that theory, so these are called weakly interacting matter particles, they interact through the weak force and through gravity. If we take this theory, then we can make a computer simulation of what the universe should look like. And do we have someone up in the box? No, we don't. All right. Okay, so this is a computer simulation of what the universe would look like if you had spectacles where you could see what dark matter looks like. And if you want to Google just the Millennium simulation, then you can see this on your computer. And yeah, that's not going to work. So this is what we think the universe would look like if you could see dark matter. So you can see that the universe has this web-like structure. And our theories predict that where you see lots and lots of dark matter, that's also where you should see lots and lots of galaxies. And if you go and look at the distributions of galaxies in our universe, they also follow this web-like structure. So that's great. But what I've been doing during my career is trying to work out a way of seeing this invisible matter, dark matter, directly. And to do that, I use a technique called gravitational lensing. Now, here's a nice little movie to demonstrate how gravitational lensing works. We have a distant galaxy, and light travels towards us to here on Earth. And in between us and this distant galaxy is a big clump of matter. Now, it doesn't matter what type of matter the matter is. It simply doesn't matter. And what you can see is that the light, as it travels towards us, gets bent and distorted. Now, that's Einstein's theory of general relativity tells us that matter curves space-time, and so as the light travels towards us, its path gets curved. And so the image of the galaxy that we observe doesn't look like the true galaxy. You can see it kind of gets bent into an arc-like shape. Here's another static cartoon to illustrate that. So what we do is we go and look at lots of distant galaxies, and their light travels towards us. I've got two clumps of dark matter here, bending space-time. And so what we actually observe when we look at these galaxies on the sky is we find that they tend to line up with each other around the clumps of dark matter. Now, this is extremely exaggerated. The effects that we're looking at are at the percent level, but basically what you're looking at is for just a very weak alignment of galaxies. So you can kind of imagine it as there's all of this dark matter out there, and it's kind of like changing the images of the galaxies behind it. It's kind of like graffitiing, I'm here, by bending the light around it. Here's an image from the Hubble Space Telescope. We go and measure the shapes of the galaxies. We look to see if they're lined up with each other, and then we can use that to map out where the dark matter is. These are the telescopes that we're using at the moment. This is the European Southern Observatory in Paranal. We're using two telescopes in tandem at the moment. There's the VISTA telescope down here and the VST telescope, which is an acronym of an acronym. It is the VLT survey telescope, which is the Very Large Telescope Survey Telescope. Don't ask me. Anyway, so the little one up here, and these are the VLTs up here. VISTA observes in the infrared, and VST up here observes in the optical. Let's zoom in. This is the telescope that we're using at the moment. This is VST. There it is on the side. And this is the camera that we're using, Omega Cam. Now, at the moment, we're mapping out two patches of the sky, in one patch in the northern hemisphere and one patch in the southern hemisphere. And just to give you, it's about a 30th of the sky that we're looking at the moment. And the data that I'm about to show you, if you imagine that you're looking up at the night sky, imagine having your kind of elbow outreach. The patch of sky we're looking at is about from your elbow to your tip of your palm. That's kind of like this patch of the sky that we're looking at. So you might think that's not very big, given the size of the sky, but it's one of the largest areas that's been surveyed to these sort of depths. And we take this data when the weather is absolutely exquisite. So this telescope is scheduled just to do these observations when the weather is perfect. Here's some of our data. So you go and you look, all these little dots are very different little background galaxies. And so you measure the shapes of the galaxies, and just in case you didn't know, dark matter is pink. There it is. So this is the distribution of the dark matter in this particular patch of sky. And all of these big galaxies, these are actually in the foreground. This is a cluster of galaxies, and you can see there's this big clump of dark matter all around it. Now, that's a very small patch of sky. I can go and do this measurement across the whole of our survey area. And this is what it looks like. This is our dark matter map in the middle, and this is just a simulation on the back to give you an idea of what we're trying to compare. So obviously our real rendition of where the dark matter is a lot blobbier than the real simulation, but you can see this web-like structure, and again we have big clumps of dark matter, and then regions where there's no dark matter, which is exactly what you'd expect from these simulations of dark matter. And if we look at where the galaxies are, it's exactly what we'd expect. The galaxies are being housed by these dark matter clumps, and so it's really the dark matter that's dictating where and when the galaxies form in our universe. Now, the astute amongst you in the audience will have made the connection that if I'm telling you there's this massive web of dark matter out there, that our own Milky Way galaxy has got a big clump of dark matter around it, that there must be some dark matter in this very room. And indeed, this is what particle physicists are now going out to try and catch and detect. If you want to indulge me this evening, just focus on the tip of your nose, just for 10 seconds. Just let your eyes go across. Embrace your inner child. Yeah, right. How many dark matter particles do you think went through the tip of your nose in those 10 seconds? Does anyone care to? 10 trillion? Yeah? Yeah? Anyone care to venture a guess? I think the naysayers at the start will have said no, none, zero. It depends on your model of the dark matter particles. The minimum is 1 million, but it could be much more than that. It really depends on the mass of the dark matter particle. But they're absolutely everywhere if our theories of dark matter is right. And so the particle physicists have got these deep undergrounds there. This is a big salt mine under the South Dakota hills. And this is where they're building the lux-zeplin dark matter detector. This is going to be the largest one to be made before they hit something called the neutrino floor, when they won't be able to distinguish between a dark matter particle and a neutrino. The reason why they're deep underground is because you want to protect them from all of the other particles. And what they're looking for is just a direct collision. So even though you've got all of these dark matter particles that are flying past us all the time, they're so small, they just don't see the particles that we're made up of. They just zip straight through us. In the time that it's taken you to come here this evening, listen to the talks and go home, there'll be at most one direct collision between a dark matter particle and a particle in your body. So the idea with these massive detectors is they fill them up with xenon and then they just leave them deep underground and just wait. And they have these little detectors inside. The dark matter particles will on occasion collide with one of these xenon particles that increases its energy just slightly, it emits a bit of light, and then they'll be able to detect it. Now, they've been doing this sort of work for a long time already, building bigger and bigger and bigger vats of stuff to catch this stuff. They haven't found one yet. The particle physicists at CERN also haven't created one. You know, the Higgs boson was supposed to be just the first thing that CERN found. It was supposed to be the first of many, many things. Particle physicists are starting to get concerned that they haven't found these dark matter particles that they would have expected. And maybe they're looking in the wrong place. Maybe our basic standard model that dark matter is a weakly interacting matter particle isn't the right way to go. People are starting to look at other particles now called axions. I hope we'll see very shortly in the next 5 to 10 years major advances in this. I hope we will find that these vats will detect a dark matter particle, because if it doesn't, we'll have to explain all of our astronomy observations which really demand that this dark matter is there. So we'll leave our dark matter story there with a sort of a challenge to the particle physicists to go out and find these dark matter particles, because astronomers have a more pressing problem on their hand, which was that big piece of the pie, dark energy. Right, how to explain dark energy? So I've put up one of Einstein's field equations, but I'm just going to blank it out because you don't really need to know what all of the formula mean. Because my point of getting it across to you is to try and explain to you where this dark energy, this mysterious term dark energy, might come from. And just a little side note, why is it called dark energy? Well, really the observation that's been made is that the expansion of our universe is accelerating. That was the main observable that was made. And when our dear American cousins were looking for funding to move this field forward, they'd exhausted NASA and the National Science Foundation at this point, so their eyes turned to the Department of Energy. And that's why it's called dark energy. I think actually it's a really bad name. But anyway, that's my version of the event, so I'm sure my colleagues will say. Right, Einstein's field equations. You can read this equation. These equations explain how things move and evolve in our universe. And on the right-hand side of the equation, we have terms that deal with the curvature of space-time. Sorry, on the left-hand side, and on the right-hand side, we have terms that deal with mass and energy. And you can read these equations in two different directions. If you read it in this direction, it says curved space-time tells mass and light how to move. And that was what I was showing you earlier with the lensing. It's the curvature of space-time that tells the light which path to take. But you can also read it in the other direction, which is that mass and energy tells space-time how to curve. Okay? Now, this little term here, this lambda here, is called the cosmological constant, and this is known as Einstein's biggest blunder. So when Einstein came up with these equations, or he called it his biggest blunder, he didn't call it his biggest blunder. Oh dear. Well, some journalists have said that this is Einstein's biggest blunder. Thank you, Sai. I stand corrected. This term was introduced to try and make the universe static. So the consequence of these equations when they came out was that the universe would be expanding. And the thought at the time was that it shouldn't be expanding, that the universe should be static. And so this additional term was introduced such that the universe was static. And then when Hubble found that the universe was in fact expanding, this additional term wasn't needed. And that's when some journalists reportedly said that Einstein said this was his biggest blunder. But this term can also act like dark energy. It was introduced to stop the expansion of our universe, but it can work in the other sense, and it can speed up the expansion of our universe instead. So this is great. We already have this problem of dark energy solved because Einstein put this additional term in his equations. But we don't really like just putting additional terms in equations. We like to understand where they come from. And the natural origin of this term in Einstein's field equations comes from thinking of what I like to call the physics of nothingness, but is also called vacuum energy. So I find this idea really, really strange. I find it really strange that nothing can have energy. So imagine you're out in the universe in one of those massive voids where there's absolutely nothing. There's no galaxies, there's no baryons, there's no gas, there's absolutely nothing at all. It's a complete vacuum. Now, quantum physics tells us that when there's absolutely nothing, actually there is something, because there is the opportunity for virtual particles to pop into existence and out of existence again. Now, when they pop into existence, they add energy to the system, and this energy can contribute to the system and speed up the expansion of the universe. And the larger these regions of nothingness are, the larger that they grow, the more opportunity there is for these virtual particles to pop into existence, give energy to the system, make it grow further, give more opportunity for virtual particles to pop into existence. And so you see we end up having this sort of perpetual motion machine where this quantum effect can cause our universe to very rapidly inflate. And it's a very beautiful theory, and it's not complete science fiction, because it has actually been measured in the laboratory. And the only problem with this very, very glorious solution to this dark energy conundrum is that our universe shouldn't exist if it is as experiments suggest it should be, because our universe should have rapidly inflated a very long time ago before the first stars and galaxies ever formed, and we shouldn't be here to witness it. And this is called the cosmological constant problem, or the vacuum energy problem. We don't understand why our universe exists as it does if these quantum effects are real. And so what we typically do is set the vacuum energy to zero. We say we don't really understand this vacuum energy conundrum, why it hasn't already rapidly accelerated our universe away. And so we're just going to say, okay, we're going to set the cosmological constant or the vacuum energy to 0. And then we're back to the drawing board to understand what this dark energy could be. And there are two types of dark energy models. There's something called modified gravity, where we modify this side of the equation. We modify the curvature of space-time. And then something which we call dark energy, so which is modifying the mass and energy side of the equation here. Okay, so that was a long introduction to dark energy, but now I'd like to have a sense of the room to see how you're feeling about dark energy this evening, because I already know your opinions on dark matter. So the question I'm going to is, what is causing the accelerated expansion of the universe? So all of the observations are pointing to the expansion of our universe accelerating, and I want you to tell me this evening what you think could be causing this accelerated expansion. So your option number 1 is that it is just this cosmological constant, and you're not going to worry about this vacuum energy stuff. You're just going to say the quantum physicists have kind of got their sums wrong. It's just low. All right, that's option 1. Option 2, a new dark energy field. So we know in the very early universe that the universe experienced a very rapid period of inflation. That's absolutely built into all of our theories of the universe. It could well be that the universe is experiencing a new period of inflation. 3, going beyond Einstein gravity. Do we need to modify Einstein's theory of gravity? Could that explain the observations that we're making? And 4, I'm just intrigued whether there are any multiverse fans in the audience. The multiverse option is that the quantum physicists have got it right. It's just there's lots of different realizations of the universe, and we just happen to be in one where the vacuum energy is kind of right for us to exist. That's your options. And again, I can see you can only vote for one. Okay? Who wants to vote for number 1, that the accelerated expansion is just a cosmological constant and we're not going to worry about vacuum energy? Okay. A small, interesting. Option number 2, a new dark energy field, a new period of inflation the universe is experiencing. Interesting, interesting. Okay, who wants to go beyond Einstein? Oh, yes, excellent, excellent. Some beyond Einstein fans. And who wants to go and meet their twin in another multiverse one day? Excellent. Do you know, I do this poll with an awful lot of different audiences, and it's no one audience is the same. It's very fascinating. So at sort of university astronomy audience, so university seminars, they're generally all voting for the first one, the simplest explanation, the cosmological constant. Particle physicists really like this option here, and the public, if I give general talk, and kids, really like going beyond Einstein. So I don't know what that says about this audience here this evening. Good. Okay, I showed you my research on dark matter. How can the work that we're doing to map out dark matter also tell us about dark energy? And what's great about the lensing technique that I was telling you about earlier is that it can distinguish between these two different ways of causing this accelerated expansion, because you're testing gravity directly. The observation that you're making is how gravity is bending space and time, distorting that light. And so you can directly test gravity theories and also different energy theories. So with lensing, you're testing both sides of that Einstein's field equation that I showed you at the start. And that's why it's one of the most important cosmological probes that we have at our disposal to make these measurements. Okay, let's think about how we're going to do this. So we've got 2 simulations now. Now the little ticky tock at the top here is time ticking down. On the left-hand side, we've got a universe with both dark matter and dark energy. And on the right-hand side, a universe with just dark matter alone. Now, I kind of like to think about dark energy and dark matter kind of like warring siblings. Right? So dark matter is the strong gravitational force. It's trying to collect everything together. It's trying to pull the structures together. And you see that it does that very successfully when it's just on its own. The structures of dark matter form a lot earlier in the universe if dark matter is just left to pull everything together with its gravitational force. Now, what dark energy is doing is it's kind of coming into the room while dark matter is trying to neatly tidy everything up together and just throwing everything apart. It's not really throwing everything apart. It's making dark matter's life much harder by increasing the distances between objects. So when gravity's trying to pull everything together, just everything's moving away further, so it takes longer to pull things together. So in a universe where you've got dark matter and dark energy, the structures form a lot later than they do in a universe with dark matter on its own. So I showed you the maps of dark matter that we're producing, but we can make those maps at different epochs in the history of the universe, just by looking at galaxies at different distances away from us. And we can use that to test how dark energy is slowing down the growth of these dark matter structures. So let's recap the method that we're using. So we're mapping out millions and millions of galaxies on the sky. We're measuring up their shapes. The cartoon here, the green ones here are the cartoon galaxies. In red, you can see the cosmic web of dark matter. And what we're looking for, the signature we're looking for, is the galaxies lining up with each other to tell us where the dark matter is. And this is the actual observable that we're measuring. So this is how aligned are galaxies as a function of their separation. Okay, so imagine if I've got two galaxies that are close to each other on the sky, their light's traveling through the large-scale structure of the universe, and it gets bent and distorted, so they're going to look like they line up with each other. Okay, so galaxies that are close to each other on the sky line up quite well with each other. And as you go to large scales, so galaxies on opposite sides of the stage, their light's travelling through different clumps of dark matter as it gets to you, so you don't see them as lined up with each other. Okay? The blue data points here are our most recent measurements from that telescope I showed you earlier in Paranal. And the different lines that you can see here are different theoretical models. Now, there's one really, really nice thing about this lensing technique is you can directly predict what you should observe. So just like those maps that I showed you right at the start of the cosmic microwave background, and I showed you that up and down curve, you can use those same theoretical models to tell you what you expect to observe. And the different colours you can see here depend on how clumpy the dark matter is and how much dark matter there is. Now, I can make this measurement at different redshifts, and remember what dark energy is doing is it's slowing down how fast those dark matter structures are clumping together. Okay, so that's what I'm looking for. I'm looking for how dark energy is changing the clumpiness of the dark matter as a function of time. Okay, now at this point, I'm going to take a little pause before I show you our results. In fact, first of all, I'll guide you around this summary plot, because it's a bit much to take in, and then I'll talk about why it says the word blind at the top here. Okay, this number on the side here just tells you about that clumpiness of the dark matter, and this here is the amount of dark matter. In green, these are the results from our most recent experiment. In grey, those are some old results that I did when I lived in Canada. And these are measurements of the clumpiness of dark matter today. Now, in red up here, this is what those first measurements I showed you from the Planck satellite, that beautiful iconic map from the smug cosmologists, okay, those are measurements of the universe right after the Big Bang. And you can use your theoretical model with a cosmological constant to predict what the clumping of the dark matter should be today, given a cosmological constant. Okay, so we're taking a theoretical model that dark energy is this cosmological constant and use those Planck results to predict how clumpy the universe, dark matter should be today. And that's this red blob up here. Now, the blue here is the previous results from the satellite before Planck. So that's something we can discuss afterwards if you want to. But at the moment, just focus on the difference between the red and the grey here in the background, which are my old results. Now, I published these grey results before the Planck satellite published their results, but only a couple of months before. And so when their results came out and they disagreed with my results, I had a very interesting summer at conferences. Now, I'm sure you've all had brilliant research careers, and you'll remember standing up in front of all your colleagues to present your results and feeling very excited about it, and being petrified about what questions you might get asked afterwards. Now, this particular summer, it was a very exciting summer because the Planck team were going around showing off their results. We were going around showing off our results. But how shall I put it? The PI of Planck is a lot more senior than me. And so he always got to ask the first question after my talk, which is, and I'm quoting, "Catherine, can you tell the audience what you've done wrong?" So you can imagine that I wished that the floor would open up and I'd fall into it. And I wasn't a professor then, so I didn't have the, well, I'm female, so I can't say balls, but you know the point I want to make. I didn't have the strength to say, "George, why don't you tell us what you've done wrong?" Okay, so that was 2013, and that was my old project that I did in Canada on the Canada-France-Hawaii telescope. And so this was a brand new telescope, European telescope, brand new team. We went back to the drawing board because I was not going to have another summer like that where I was being asked what we had done wrong. And we did everything from scratch. It's very complicated, this measurement that we made, and Justin, who's going to talk afterwards, will give you more of the sense of just how challenging this actual measurement is. We went back to the drawing board and we went through absolutely everything. We upgraded everything we did. I feel very confident with our results. But I also had this inner feeling that I really, really, really wanted to agree with the Planck team, which is not good science. I'm sure you'll all agree. That's not good science. So this is why it says the word blind here, because my colleagues realised that I really wanted our results to agree with Planck, and that therefore we had to do something such that when we did publish our results, we were confident that they were what we were getting from the data and not biased in some way by something I'd done to the data as we went along the way. So what we did was we blinded our data. We created 3 versions of our data. An external person from the team did this for us. So we handed them our data. They sent us 3 versions of the data back. 1 was the truth, 2 was sabotaged. This was our first blind, so agreeing with the previous results that we had. This was our second blind, so in even more disagreement with the Planck results. I really didn't want this one. And this was our third result, which was, that's okay, that's reasonable, good agreement between the two, and you know which one I wanted. It was very exciting. We wrote 3 versions of the paper. We sent our papers off to our external. He replied back to say which one was the truth, and we published very soon afterwards. And this is the truth here. A 2.3 sigma tension between our results and the iconic Planck results here. Right, what does this mean? If you say, I have a 2.3 sigma tension to an astronomer, they go, "Whoa." But if you say that to a particle physicist, they go, So what we need to do now is to shrink our error bars. If these error bars shrink, and you see more of a distinction between these Planck results and on our results, then that tells you something very interesting about dark energy, because let's just remind ourselves, this is what we predict the clumping of the dark matter should look like today. If dark energy is a cosmological constant, and it's saying that it should be clumpier than we're actually measuring. So that suggests that there's less dark energy than this model suggests. Interestingly, we are not the only group who disagrees with the Planck results. This is a compilation of measurements of the Hubble constant. Now, I'm sure a lot of you will be familiar with the story of the Hubble constant. Hubble tells us how fast the universe is expanding. There were 2 competing camps long in the history of these measurements, and this is a nice compilation plot by Wendy Freeman, where she looks at how the measurements of the Hubble constant has varied over time. And you can measure this directly using Cepheids, these are these blue points here, or you can measure it again from the cosmic microwave background. I mean, it's absolutely amazing what you can do with the CMB measurements. And you can see as the error bars tighten, we've again got a discrepancy between the 2 measurements. So the rate of the expansion of the universe, the Hubble constant today, as predicted by Planck, using a cosmological constant for your dark energy, gives you a different result than direct measurements of the Hubble constant. So it's very interesting times. Is this a sign of new physics? Or is this that we just haven't quite got our observational analysis right yet? And that's what we're all working on very feverishly. There are 3 projects on the sky at the moment. I've just told you about our one, which is the European project, the Kilodegree Survey. But there are also 2 other experiments doing very similar techniques to us. There's the Dark Energy Survey, which the UK is heavily involved in as well. And then also a really fantastic instrument called the Hyper Supreme Cam in Japan. This is a really, really exciting new instrument. And at the moment, these 3 are competing on the sky. It's going to be really interesting to see if we get similar results. DES have published their first-year data, and they are also on the low side compared to Planck. So really interesting times. But what's happening next? Well, these are some observations that were taken in some of the best observing conditions in Paranal in Chile. And this is what it's going to look like. This is what it looks like from space. So it's like just putting on a pair of spectacles. And if you're looking for that very weak alignment of galaxies, then going up into space really helps with that. So there are 3 telescopes on the horizon in the 2020s that are going to be working in tandem with each other. There's 2 space-based telescopes, Euclid, which is a predominantly European project, but with US involvement. It's a 1.2 meter telescope that's going to produce Hubble space-like quality images across the whole sky. It's going to be absolutely beautiful. And WFIRST is an American project with some UK involvement, which is looking at a smaller patch of sky. And these 2 are going to be looking above the atmosphere. But at the same time, a project that I'm more excited about, because I'm more involved in it, is called the Large Synoptic Survey Telescope. It's an 8.4 meter telescope that's going to be constantly surveying the sky. Now, here's another lesson for us to learn from our US colleagues. They were very excited about dark energy. They loved this lensing technique. They really wanted to design an amazing telescope to go out and measure it. The ultimate telescope is an 8.4 meter telescope that images the whole sky every 3 nights over a 10-year period to build up a really deep depth. Did they sell it to Congress like that? No. They're going to find killer asteroids. And it will actually find killer asteroids. And actually, that is a major science component of LSST. But it is also going to give us the most exquisite data set to make these maps of dark matter, to look at how dark matter is evolving with time, and to really confront these different theories on the dark universe. And what's really interesting is the combination of all of these 3 together, working in tandem. I really think we're going to be able to really understand what's causing this accelerated expansion of the universe. When are we going to know if a cosmological constant is the right model? Well, there are already hints in our data that maybe it's not, which we need to investigate further. But in the next few years, those error bars are really going to shrink. And so if it's very wrong, if the cosmological constant really isn't the right model to explain dark energy, you're going to know about it quite soon. LSST, Euclid are going to be measuring the dark universe to very high precision by about 2025. So it's not long before we'll see the results from these new exciting pieces of technology. So if it's slightly wrong, you're going to know about it on that timescale. What's maybe more concerning is many dark energy and modified gravity theories actually look very similar to a cosmological constant. And my fear is that we might never know. And so for the young members of the audience that I see out there, I strongly encourage you to come up with some very neat ideas about how we can distinguish these different models from each other. Because if it comes out that really the answer is the cosmological constant, then we're really going to have to understand this whole vacuum energy thing. And I really hate the conclusion of my whole life's work to be that we live in a multiverse. That would be a bit disappointing. 3 things I'd like you to go away and tell your friends. The universe is filled by a giant invisible cosmic web of dark matter, and I've shown you some maps of that this evening that we've been able to make using this lensing technique. The expansion of the universe is speeding up. We don't know why, but we're building some amazing experiments to go out and find out the answer to that. And the reason why you should care, and the reason why I'm so delighted that you've been all paying so much attention this evening, is because our final understanding of all of this dark stuff in the universe, I believe, is going to have to involve some sort of new physics, because we can't explain it with our current model of physics. And it's widely believed that that's really going to change our view of fundamental physics. Thank you very much.
Okay, thank you, Catherine, very much, and super timing. We've got time for questions, so let's have some questions at the back. Margaret.
Can I just point out that there was at least one early measurement of the Hubble constant, which nobody ever mentions. That was the IUE satellite observed the double quasar, so it's gravitationally lensed, so you've got two images of the same galaxy, and so you've got two ultraviolet spectra of the same object. And that was analysed by, I think it was Bob Wilson and Parag Gondalekar. And they came up with an answer, like if I say 74 plus or minus a small number, it was a small error bar, then it is entirely consistent, I think, with anything serious that's been done since. But I really think people should look at it again, because it's a unique way of doing it.
Well, thank you for that, because people are actually doing that. Which is brilliant. So there's a fantastic team. There's Sherry Sue, Frederick Corban, who are working on exactly that question. So it's the same lensing technique that I was telling you about. So the idea is you have some foreground clump of matter, and you have some variable source behind it. So some quasar that's turning on and off. But the light from that quasar takes two different paths to get to you. One will be slightly longer than the other. And so you get a time delay between the two objects, between the two images. And that allows you to constrain the Hubble constant. Now, it's had a revival recently, partly to address this question, because you've got two different measurements now. You know, the Planck measurement is extremely clean, but in order to be able to infer a value of the Hubble constant, you need a cosmological model. You need to have a model for dark matter and dark energy. Whereas these direct measurements from the Cepheids and the Masars is a direct measurement. You don't have to have a cosmological model. So people wanted a third method. And using these time delay methods, these strong lensing time delays, then they can measure that. And what they're finding is, and I should have got a better plot, but it's around, they're finding a measurement just around here. So it's not completely inconsistent with the Planck results, but it's in tighter agreement with the Cepheid results up here. And they're now doing very dedicated monitoring campaigns to get more of these lenses. And the LSST project that I showed you at the end, so it's going to find these killer asteroids, which is going to be brilliant, but basically it's going to find anything that changes in time. So it's going to show you where all of the quasars are, it's going to show you where anything that's sort of varying is, it's going to produce all of these strong lensing features. And so there's so much science that you can do with that project that will be able to address this question. So yeah, thanks for letting me tell that one.
When you took... When you took your second poll,
Yes.
you said vote for only one. Could it may be that there is a cosmological constant and some modification of GR? As
So-
well, you know, I mean, just to complicate things.
Okay, so for me, a cosmological constant equals vacuum energy, and one can argue about that or not. I think solving the vacuum energy problem is easiest by just setting it to zero. Like there are mechanisms you can do to set it to zero, but to set it to a non-zero and small value is hard. So I think you either say, okay, it's something to do with vacuum energy, or I'm going to set it to zero and then I'm going to have some other mechanism. Yes, in principle you can have both, but there only isn't the best solution, the simplest answer. So it's hard. So what I didn't talk about today was gravitational waves, because I was hoping we'd have another gravitational wave speaker. But actually the tightest constraints now on these beyond Einstein modified gravity theories come from that amazing result where they saw a gravitational wave coincidence with an optical source. And that means that the gravitational wave is traveling at the same speed as light. And that actually puts extremely tight constraints on different modified gravity theories that can produce an acceleration like dark energy. And so actually the modified gravity community at the moment are really scrambling to say, okay, what viable models are left that are not ruled out by this gravitational wave result, but still give us acceleration. And there are a couple that are left, but they're extremely complicated models. They're by far not the simplest model that are there. And so I would have voted, before that result of the gravitational waves, I would have voted with you guys on beyond modified gravity theories. But since that result's come out and really ruled out a lot of these models, I'm finding myself more turning towards looking at different scalar field theories, different dark energy theories. Yeah.
Several years ago, when there existed what people call the solar neutrino problem,
Yeah.
one explanation that was favoured in some quarters was WIMPs congregating in the centre of stars.
Mm-hmm.
Why should they not?
Why should they not congregate in the centre of stars? I don't think they should not. So if you look at the sort of the profile of dark matter particles, they do, well, some of them have what we call a cusp in the middle. So there are lots of WIMPs in the centre of galaxies and stars. Actually, in the centre of stars, I haven't actually thought about that one.
This would mean that our estimates on mass and things like that are all, and the structure of stars are all...
Yeah, I think so.
Wrong.
So one way, one way to picture it is, say if this was the dark matter halo around a galaxy, the actual galaxy that you can see is a tiny pinprick in the middle. So just thinking on terms of scale, just the extent of the dark matter relative to the stars that you can see in the galaxy is just so much larger. But yeah, I mean the dark matter is absolutely everywhere. There's so much more of it, but it's also much more spread out.
Mike, a question.
Thanks. So the microlensing surveys, the analysis is extremely statistical in its basis. And if you're measuring a whole lot of probability functions that aren't Gaussian, is there any chance that is skewing their results in a kind of systematic way from one survey to another, simply because the things you're measuring are perhaps not distributed in a Gaussian fashion?
Okay, so so I didn't talk about microlensing. I talked about it very briefly. So the idea is if you have lots of, if you look at a patch of sky, then if there are any sort of clumps of matter in between you and the stars in the background, then if it goes in front of your background light source, then it will magnify it, and that's the same lensing effect. It just bends the light, and so you see sort of distant stars increase their brightness and then decrease again as something goes in front of it. And actually, this is the technique that's been used to find exoplanets as well, as you have something that orbits the star. So the microlensing searches to try and see if dark matter could be explained by having lots of dark stars in our own galaxy really didn't find anything, but they paved the way for a lot of this exoplanet search. Now, I think your question was about Gaussian probabilities, which I'm not sure what you were asking about, but just whether, I think just they've been observing for so long now, I think they must be reaching the point where they really understand their errors and their analyses. But I'm not sure I understood your question.
I realise there are other questions, but we're going to have to move on again, I'm afraid. So thank you very much, Catherine.